Hello everyone, welcome to the second video of Edexcel GCE Physics Unit 1, June 2017 solution. We have done 14 questions in the last video. Let's start from question number 15. So question number 15 says, a jet ski is a jet-propelled vehicle that moves across the surface of the water. So the, to propel the jet ski forward, water is drawn through an intake and then ejected through the water outlet at high speed. This is the water intake, and from this water comes out. Okay, so explain why the cross-sectional area of the water outlet is smaller than the cross-sectional area of the water intake. So what happens if a fluid, or in this case it is a water, when water flows through a pipe, it flows with a constant rate. Remember, rate of flow rate of flow of water is constant throughout. It should be constant. Okay, so meaning if one end is wider than the other, or the other is narrower, that means in order to keep flow rate constant, the speed from the narrow end should be greater than the other end. That's the only way when the rate of flow remains constant. That's how when the water goes in, it goes in with the slower speed. When it is comes out, it is a narrow end, it comes out with the high speed. That's how you can write the answer. So when water flows through a pipe, the rate of flow of water remains constant. So in order to maintain the rate flow, so it should have greater velocity from the narrow pipe. AII, explain using Newton's laws of motion how ejection of water at high speed results in the forward propulsion of the jet ski. It is the typical questions of Newton law. We apply generally Newton's third law, that one object apply force on the other, then the other object apply force on the first, and then we have a resultant force. So the, the object moves. So in this case, we can say that as water is coming out from the backside, so the jet ski is applying force on the water jet. And according to Newton's third law, the water jet apply force on the jet ski. And Newton's second law says we have a resultant force, so it moves forward. So you can write this typical answer. The jet ski applies force on the water jet, and the Newton's third law says the water jet applies force on the jet ski should be equal and opposite. And Newton's second law says because of the resultant force, it is moving forward. So it's a 3-mark question. Okay, so a man on jet ski is heading away from the coast at a speed of 90 meters per second in a direction 30 degrees south of the east, as shown. Okay, that means, okay, fine, this is the direction of the jet ski. There is a current in the water of 6 meters per second due north. Okay, so north is this. Fine. The velocity of the jet ski has been drawn to scale on the vector diagram below, with the scale 1 meter per second 0.5 centimeter. Okay, this is the scale to draw the vector diagram. Complete the vector diagram and determine the resultant velocity of the jet ski. So what you need to do, first you need to find the scale for 6 meter per second according to this. So you will say that 1 meter second inverse is equal to 0.5 centimeter. That means 6 meter second inverse must be equal to x, and from this you can have x is equal to 3 centimeter. So use your ruler protector, you need to draw a vector in northward direction for the stream of water, 6 meter due north. So joining with the head of the first vector, you draw the second vector perpendicularly, okay? And I'm drawing with the hand, so it's but you should use ruler. So it is a 3 centimeter line northward showing 6 meter per second, and then you join uh, tail of the first with the head of the last with the ruler, and this new line will show the resultant velocity, and you measure the length and then convert it into the velocity, and then you need to find the angle from the horizontal, so that will be angle theta, showing the direction of the jet ski. If you follow all the steps, then you must have the diagram like this. You can see this 3 centimeter is the corresponding vector for 6 meter due north, and joining the two vector, you have a resultant, the red one, and the length, for me the length was 8.3 centimeter. When you convert this 8.3 centimeter as per this scale, you can have the resultant velocity, but for me it is 16.6 meter per second, and the angle is 13 degree. This angle is, remember, I am measuring from the east. From the east mean this angle. Okay, so question number 16. The picture shows a machine to launch tennis ball used by a tennis player when training. The following information appears on the manufacturer's website. The launcher features an adjustable trajectory from uh, minus 20 degree to 18 degree. A ball speed range from 5 to 38 meter, and the ball capacity of 25 balls. Okay, the launcher is initially set to release balls at a speed of 30 meter per second at an angle of 25 to the horizontal. State and explain two ways in which the launcher uh, can be adjusted to increase the time of flight. Okay, if you see the time of flight depends on two factors. Number one, projection velocity, velocity of projection. If you increase the velocity, you will increase the time of flight, or angle of projection. That means projection angle. And in fact, the time of flight depends on vertical component. Vertical component means this is the projection velocity, this is the angle. And if you remember, in projectile we define vertical and horizontal components. So this is vertical component, and this is horizontal component. So horizontal components of the velocity. So if you can increase the vertical component, and vertical component, if you remember, the formula is u sine theta. So u is initial velocity, theta is the angle of projection. So you increase any one of these, you can increase the time of flight, because increasing theta can increase the range, and u also can increase the time of flight. That's how you can incorporate all these comments like these. The time of flight depends on initial velocity and the angle of projection, and you can increase the initial velocity to increase the vertical component, or increase the angle of projection to increase the height, so the time of flight. B. Calculate the maximum power output of the launcher. Time taken to release tennis ball is 0.9 second, and the mass of the tennis ball is 0.058 kilogram. So you need to calculate maximum power. So remember, maximum power uh, depends on the maximum speed, and if you go back, its maximum speed is 38 meter per second. So you can say that at maximum speed at 38 meter per second you will have maximum power. So you can say that power is equal to energy upon time, and basically this energy would be half mv square, and v you can use 38 meter per second to find the energy, and time is given 0.9 and mass is 0.055. So you put half mv square here, and T you can have maximum power, which is equal to 46.5 watt. This is the maximum power. Okay, so part B, the diagram shows a plain view of the tennis court during the tennis match. Detector placed on the court can record the speed of the player's serve. A detector placed at the end of the court in the line with OA. This is OA. Okay, and it measures the speed of the ball toward the detector. So ball is coming from O toward the detector. A tennis ball is served by a player from the position O to the direction OB. This is O and this is B. That means player served the ball in that direction. Okay. Explain why the detector records a velocity that is less than the actual velocity. Because detector is placed along with the line OA, and you see for the velocity you have two components. You have a vertical component and you have horizontal component of the velocity, meaning, I'm sorry about my drawing because I'm not using the ruler. So this is horizontal component VH and this is vertical component VV. So the detector is only detect horizontal component, not the vertical one. That's why you have um, less velocity detected by the detector than the actual one. So you write that the detector uh, the detector will detect sorry about that detect only horizontal component of the velocity. That's why it is less than. Okay. Next, using the value given in the diagram, calculate the percentage error in the recorded velocity. So in the diagram, which is this, so you need to calculate the percentage error. So you have two choices. One, you can calculate the velocity and then actual velocity and recorded velocity, and you can find the percentage error. For me, it's easy to find the distances because if you see, it's 8.3 and it is 4.1. So you join O with the D, and then you can say, okay, fine. You have, sorry, it's wrong. That means, okay, that means from O to D, and then if you join these, see, you have a right triangle. So you have adjacent side, you have opposite, so you can find the hypotenuse using Pythagoras theorem. So once you find the hypotenuse, which is of course OB square is equal to OA square plus AB square. Once you do this, you have OB is equal to 18.8 meter. It is 18.8. And then for percentage error, percentage error, you do OB minus OA, which was the actual um, distance from detector, and divided by OB. If you do this, you have percentage error equal to 2.4%. Let's see, question number 17. A coin is dropped from the top of a tall building. The coin may fall in either position X or the position Y, landing a time t after being released. The drag force D acting on the coin is given by D is equal to half of C rho A V square, where C is a constant called the drag coefficient, rho density, A is the area of cross section perpendicular to the direction of the travel, and V is the terminal velocity. So at terminal velocity, the magnitude of the drag force is equal to the weight of the coin. Okay. Explain which position of the coin X and Y would result in a smaller terminal velocity. Okay, so as per given condition, yes, at terminal velocity, drag force is equal to the weight. If you see, if you rearrange, the velocity is square is equal to 2b over rho A and C, because no matter you are using position X or position Y in dropping, at terminal velocity for both, weight is equal to the drag, or drag is equal to the weight. So in both cases, drag would be same. That means velocity will not be affected by the drag. It is constant for them. That means V square is inversely proportional to the area. So V square is inversely proportional to the area. That means greater the area, less the terminal velocity. So of course, for position X, you have a greater area. That means for position X, you have a less terminal velocity. So you can write your answer like that. Okay, so next part B I. The coin falls into position X as shown. Okay, diameter and thickness show that the terminal velocity of the coin is about 15 meters per second. Assume that the upthrust on the coin is negligible. So C is given, rho is given, weight of the coin is given. So if you rearrange your equation and you say that V square is equal to 2D divided by C rho and A. So in place of D, because it's all about terminal velocity, D can be replaced with the weight, and area you can find pi D square by 4. If you use area for this, diameter is given. Remember, this is your diameter. You put diameter here, divided by 4 after taking square, and pi, you have area. Rho is given, which is 1.2. If you see, C is also 1.1, and weight is 0.048. And you find the V. So when you do this calculation, your velocity, terminal velocity, would be equal to 14.5 meter second inverse. Okay, so I, part II. A second identical coin is pushed horizontally off the top of the building with an initial velocity of 0.60 meter per second. Calculate the distance from the base of the building that this coin will land. Assume that this coin also falls in the position X and reaches terminal velocity almost instantly. Height of the building is 305. If you sketch the situation, so you have a building from the ground, and height of the building is 305, and you are flipping a coin horizontally with the velocity of 0.6 meter second inverse, and the coin will land something like that. Finally, you need to find the distance from the base. This is your prime requirement, which is the horizontal distance. So horizontal distance is all about the projectile. You know that the horizontal distance you need to find, so you need to use S equal to UD. U is the horizontal velocity, which is given. You can use 0.6. You can find the distance, but you don't have time. And for the time, you are given this vertical height. But there is one important catch, if you can understand. They are saying the coin reaches terminal velocity almost instantly. That means the vertical velocity is also constant. It is not increasing, it remains constant. And you have calculated the vertical velocity, which is 14.5. So you don't need to use equation of motion. You can use a uniform motion equation for vertical motion as well. So first what you do, you use V is equal to distance upon time. Here V is and T is equal to distance upon V. And it's all about, remember, vertical. Because why am I using this? I'm the coin is falling with the terminal velocity, so it is not changing. That's why I can use this formula. T is equal to S upon V, and S is 305, which is the height of the building, divided by V. V I have already found, 14.5. Here, if you do that, the time would be equal to 21 seconds. And I can use this time in my equation for horizontal distance. So S is equal to U. In this case, U, I'm going to take horizontal velocity, which is 0.6, I guess. Yes, 0.6 times time, and time is 21 when you solve this. So S is equal to 12.6 meter. This is the distance of the coin from the base of the building. Part C, a student claims that the small coin, if dropped from a tall building, can cause serious injuries were it to land on the person. A second student claims that this would only be a case had the coin been falling through the vacuum. Show that the coin falling through the distance of 305 meters through a vacuum would reach the ground at the speed over 5 times faster than the coin falling through distance through the air in position X. It's a simple case. You just consider that the coin is falling through a vacuum, that means you can say that initial velocity of the coin you can consider is 0, and it is falling through vacuum, so no drag is there, so drag is 0, so meaning acceleration is 9.81 meter second minus 2 or Newton per kg, and distance or height travel is 305 meter, and you need to find final velocity, the new velocity in vacuum, which is question mark, so you can use v square is equal to u square plus 2as. If you use this, you can find that v dash is equal to 77.4 meter second inverse, and because you need to compare, that means v dash divided by v, which is equal to 77.4 divided by, this is the velocity through air, which is you have already calculated 14.5, and if you divide you can have 5.3, the ratio between these two velocity. So v dash is in fact approximately 5 times of v. Okay, question number 18. Orthodontics use braces to straighten a patient's teeth. The force required to move the teeth and the distance to the teeth need to move both depend on the individual patient. One type of braces consists of a wire under tension placed across the teeth, held in place by the brackets on each tooth. Braces is fitted to a patient and tightened, and the tension in the wire is 18 Newton. Okay, this is the diagram. Calculate the total force of the wire to the tooth to move to the tooth in the direction shown. Okay, so meaning we need to find the total tension in downward direction. So if you consider only half of the diagram, so you can say that you have tension 18 Newton, and you can resolve its two component. It is a, you can say till here you have downward component, rightward component, and this angle is 20 degree. So you can say that this downward component is basically t sine 20, and t, remember this t is the tension, which is 18, and you have a two wires, left side and the right side. So the total force for the wire is total force is 2 times of 18, which is, you can see it is t sine 20, and if you calculate this, the total force F is 12.3 Newton. Okay, so this is total force in downward direction due to these two wires. So this is part AI. Part AII explain why the wire will not produce any movement of the tooth perpendicular to the direction of shown. That means why these wires cannot produce any motion perpendicular to the wire like these. If you see the diagram, you have a two component of the tensions. This is the perpendicular motion, but for the tension you have two component, and these two perpendicular components are in opposite direction. That's why they are cancelling, so there's no net force in in these direction. That's why they will not produce any movement of the two perpendicular to the direction shown. Part B, the wire is already under tension when it is inserted into the bracket. Calculate the extension of the nickel titanium wire when under tension of 18 Newton. Young modulus of the nickel titanium is this, original length is this, cross-sectional area of the wire is this. Okay, so if you say, because Young modulus is given, we need to find the extension. We need to find extension. That means since y is equal to stress over strain, or you can say you have fx into a delta x, and you need to find this delta x. So you can rearrange, you can make delta x as a subject. So delta x, that means extension, is equal to f x divided by area into y, which is a Young modulus. So you can see in this formula everything is given. Force is a tension, which is 18 Newton. X is original length, which is x. This is f. This is x. Area is this, and this is your Young modulus. You can substitute all the values and you can calculate delta x. So delta x would be equal to 2.84 into 10 raised to the power minus 4 meter, because it is extension. Okay, let's say this is part C, and both nickel titanium and stainless steel wire are used in braces. The stress strain graph for nickel and stainless steel up to the fractures are shown. Stainless steel and nickel titanium stress strain graph. Complete the table to compare the properties of the two wires using evidence from the graph. The first line has been okay. So we need to compare both the wire. So the first steel is a stiffer, because of course it is a stiffer gradient, and you can write many points. At least you can say that stainless steel is a stronger, because it's stronger than nickel titanium, because it is bearing a large amount of stress than the nickel titanium. So steel is stronger because of large stress. Or you can say that stainless is less ductile, or it's better to say that nickel is a ductile, because it has a large plastic deformation, and large under area shows that nickel also has is a tougher material than the steel. Okay, so that's how you can write. So nickel titanium is tougher than steel because of the large area, showing large energy absorbed. Steel is stronger because of large breaking stress, or yes, large breaking stress. You can say large breaking stress or large amount. Nickel titanium more ductile because of large plastic deformation. Suggest how the type of the wire the orthodontist uses depend on the individual patients. So type of the wire depends on the tooth. So if tooth is difficult to move and required large amount of force to move, that means the dentist is going to use steel wire. And if there is a large gap between the teeth, then because large distance need to be traveled for the teeth, so large distance means large deformation. So nickel titanium wire is good to use. So you can combine all these points, and you can write teeth are difficult to move, that means greater force is required, and then the steel wire is going to use. And if the teeth need to move for a large distance, large gap is there, that means nickel titanium because of the large strain. Okay, that's it. Thank you very much. We have done all the question from Edexcel GCE Jan 2017 Physics Unit 1 paper. I hope you understood all the condition. Thank you very much. Thank you for watching. See you in the next video. Bye.